Hey Radical Scientists, this is Mr. Giovanni with another series of problem walkthrough videos as we wrap up not only this unit on forces in motion, but also our year of learning here as a community. Now, as we are wrapping up things, as we are looking at some of the last problems and preparing for our one and only practice, our one and only test, I wanted to be really explicit about the intentionality that I've had as we are looking at more and more math at the end of the day in this unit. On one hand, I do want us to get that preparation for how physics will normally be assessed in spaces outside of our classroom, but to be also transparent, I'm also have this goal in mind about not only being able to learn how to solve specific problems like we've been doing all year with these videos, but to also support the development of a problem solving strategy that will really center the learning process as a whole. I will be trying to be clear about what type of process that I'm trying to support in some of these example problems, but at the end of the day, what I'm really trying to I think convey is that while it can be pretty overwhelming to look at a lot of physics problems, for example, at a time and be like, I have to learn how to kind of do this problem in this specific way, truly, I ask us to truly take a moment to think about how math can be a tool that at the end of the day we can use to manipulate, right? Different situations with different little variables or circumstances allow us to really think about what is in our current situation and how do we actually use those tools to apply it. And in this case, I hope that we can develop a type of confidence where we're not looking at these problems and feeling overwhelmed about how much do we know, how much will we get done, and just thinking of each problem as an opportunity to test the actual skill of translating, applying some type of equation, and ultimately solving for what we're looking for. And once again, simply including that message to really emphasize how this applies even regardless of the type of problem we're looking at, right? Without further ado, here is our third problem for this series. And here we go with one other problem to practice with, which again, for your reference, I'm including here the assignment under which you can find this problem, right? We've already seen this, but for our own sake, for our own practice, right? Let's try to approach this without that context to see if we can really translate this with our equations. First things first, what are we looking for? A net force of 1,250 newtons acts on that 75 kg object. How much would the momentum change after 8 seconds? How much would the velocity change after 10 seconds? Here we have two questions, and with them seems like two different scenarios to work with, right? The first question, which we'll focus on first, asks us how much would the momentum change after 8 seconds, right? How much would the momentum change? The momentum is expected to change. We don't know how much, what that quantity is, right? This delta, which symbolizes change with the p, the momentum, is not known and is what we're ultimately looking for. And after we know where we're supposed to be headed towards, right, with these problems, we can ask, what do we know? And here, a couple of numbers for sure must be underlined. That 1250 newtons, that 75 kg, and those 8 seconds. These three numbers are provided for us and might relate to our ultimate quantity. And in order for us to really think about that, I'm going to go ahead and start writing some of this. 1250 newtons, that newtons indicates some type of force quantity. I'm going to write that right under here. 50 newtons. 75 kg, that's a mass units, a mass quantity, so I'm going to write that under our m. And for our initial time for this first problem, I'm going to put a 1 there. I'm going to go ahead and write 8 seconds. 25 kg, 1250 newtons, 8 seconds. Here, once I have some of the stuff I know and what I'm looking for, we can look at equations that might relate delta p with these three quantities in our practice formulas. Now, I see delta P coming up in how it relates to two different types of problems. It seems that delta P over T relates to force, and it also relates to M delta V and T on the right. But because I don't recall reading anything about a velocity change, I'm going to go ahead and play it safe and just stick with the F equals delta P over T. Maybe that might change in a bit, but for now I know that these three different values are stuff that I know. F is equal to delta P T. F is equal to delta PT, an equation for reference. I'm going to go ahead and start substituting that with things I know. I know that the force is 1250 newtons on the left. Our delta P is something we're not quite sure of. We're going to be looking for that, but that's okay. We have all other values, including the time, which is 8 seconds. And here we see that this 8 seconds is related to this P through division. Right, on the denominator, we need to multiply this by 8 seconds. If it helps to think about it this way, numerator denominator should give us a 1. Anything over itself is 1. But something different changes when we multiply it over here. That 8 seconds must be multiplied with the 1250, right? And the newtons, to be super clear, I'm going to write over here, the newtons are an abbreviation for kg meters over second squared, which means that if a second is being multiplied and there's the second in the denominator, two of them, one of them is going to be simplified to just kg m, just one s, not the 2, because that other was cancelled out with the s. But the 8 and the 1250 still are related. 8 times 1250. This time I'm just going to multiply with my physical calculator, y'all. 1250 times 8 gives us a perfect 10,000. Y'all can calculate this in your own calculators. 10,000 kg m over s equals what is at the right, just our delta P, right? No other steps necessary for this. Delta P is equal to 10,000 kg m over s, which is in fact the unit for momentum. Take a moment to appreciate what we've done so far, and also recognize that there is a second problem to also attend to with the same exact steps here. So it's kind of a 2-for-1. The second question asks us, how much would the velocity change after 10 seconds? How much would the velocity change? What am I looking for? It's asking me how much, and expecting me that there's going to be a velocity change to think about, right? Some type of delta V that we do not know. When we think about the second question, what do we know? Here we also recognize that one of these different quantities has changed. In this question, they're actually giving me a different time to work with. The time being 10 seconds. Whatever quantity delta V will be, it must account for a time of 10 seconds. While all other forces, all other values, like the force here, still remain the same. Nothing has been said about them, so we can work with the same quantities, right? Here, once again, I want to think about how am I going to relate all of these together? How am I going to use an equation to connect all of these and have something to solve? Delta V, T, F, and M, right? And in this case, I noticed that it's going to be a little more useful actually if we think about the M delta V equals all over T equaling our F quantity that we know as well. So I hope it's not too complicated. Let me scroll down a little bit over here. Let's go ahead and focus now not on the middle segment, but instead on this M delta V over T. I'm going to go and rewrite it here. In fact, F is equal to M delta V over T. These values on the left, on what we know, seem to be connected with these, and I can even start substituting them in, right? 1250 newtons is equal to some type of mass, in this case 25 kg, right? Time delta V we don't know, but we will solve, all over 10 seconds of time. with these numbers in mind, we can start thinking about what to do first. There might be a different series of steps. I'm looking at this 10-second denominator. I'm going to go ahead and multiply that first, just as preference, right? Those 10 seconds, as we saw before, should ultimately give us cancel out the newtons. We're going to add just 1250 because we're only multiplying by 10. 500 actually, kg m over s equals, this turns out to be 1 over here, 25 kg delta v. And this delta v is related to this 25 kg of mass through multiplication. So to continue on with the mass, I can go ahead and divide this by 25 kg, divide this by 25 kg, and I recommend that the number will have to calculate with a calculator, but the kgs for sure will cancel out. This will be left with the meters per second unit, which is something we expect. So we cancel this out, and this is a 1. A delta v, right, that delta v should be in units of meters per second. What will 12,500 divided by 25 be? I am getting in my calculator 500 meters per second difference. 500 meters per second difference. The velocity changes, delta v, is equal to 500 meters per second for this second problem.